Hi everyone. Imagine we're in a market where the only cash in circulation consists of 3-cent coins and 5-cent coins. Also, let us assume that change is allowed in a transaction. Now, if a toy costs 7 cents, will the purchase be completed smoothly? In other words, we're asking, do there exist integers x and y such that 5x plus 3y is equal to 7? Equations like this are called linear Diophantine equations. In this section, we will study the existence of integer solutions for linear Diophantine equations. To start with, let us look at the definition of a linear Diophantine equation, which is an equation of the type ax plus by is equal to c, where a, b, c are all integers. Here, be careful, we only care the integer solutions of this equation. Our first result is about the existence of the solution, as is given by the following proposition. A linear Diophantine equation has integer solutions if and only if the greatest common divisor of a and b divides the integer c. Let us first prove the necessity. To this end, let x now, y now be integer solutions of the equation, which means that ax now plus by now is equal to c. Now, by definition, GCDAB divides A, hence it divides AX now. Similarly, GCDAB divides B, therefore BY now. Adding these two together, we see that GCDAB divides AX now plus BY now, which is precisely C. Thus, the forward direction of the proposition is proved. For the other direction, let us assume that GCDAB divides C, which means that c is equal to k times GCDAB for some integer k. Now, recall the Bayes identity claims that there exist integers x and y such that ax plus by is equal to GCDAB. Multiplying the integer k on both hand side, we see that a times kx plus b times ky is equal to k times GCDAB, which is equal to c. In other words, if we denote by x now and y now the integers kx and ky respectively, then x now and y now will serve as a pair of integer solutions of the original equation. This finishes the backward direction of the proposition. As an easy application, let us review a proposition that we have proved previously, which claims that given integers a and b not both 0, if we use their greatest common divisor to divide a and b respectively, the remaining quotients will be co-prime to each other. And also recall that we have proved this using the definition of the greatest common divisor. Now, we will try to provide an alternative approach to this proof using the linear Diophantine equation's existence result. More precisely, we know that there are integers x now, y now, such that ax now plus by now is equal to GCDAB. Now, dividing GCDAB on both hand side leads to a over GCDAB times x now plus b over GCDAB times y now is equal to 1. And if we consider a over GCDAB and b over GCDAB to be new integer coefficients, namely a bar and b bar respectively, and consider the new linear Diophantine equation a bar x plus b bar y is equal to 1, then clearly x now and y now form a pair of integer solutions for this new linear Diophantine equation. And due to the proposition we just proved, the greatest common divisor of a bar and b bar must divide 1. In other words, it must be 1. And if you recall the definition of a bar and b bar, that is precisely the proposition we're looking for. As you can see, this new approach might be slightly more concise compared to the previous proof based on the definition. Alright, we have now seen the necessary and sufficient condition for the existence of integer solutions of a linear Diophantine equation. In the next section, we will discuss that given the existence of solutions, how can we find all solutions of a linear Diophantine equation?